You are sitting quietly in a room when a thin blade of sunlight slips through the window and stretches across the floor. You can see it floating through the air, especially where tiny particles of dust drift through the beam. It seems smooth, continuous, almost like a physical ribbon connecting the window to the opposite wall. Or imagine turning on a flashlight in a dark room. A narrow beam appears almost instantly, traveling cleanly through the darkness. To your eyes, there is no obvious break in it, no visible pieces, no tiny gaps. Light simply looks like light. And yet, something strange happens when you stop looking at the beam as a whole, and instead watch what happens when light actually meets matter. A photon reaches a surface. An electron absorbs energy. A detector registers a tiny, localized event, not a faint miniature beam, not a smaller version of the glowing line you see crossing the room. A single interaction. This is where our ordinary picture begins to become uncomfortable. Because the light entering through that window can spread across space in a way that looks beautifully continuous. It can behave like a wave, producing interference and diffraction, but when its energy is transferred to matter, the interaction can occur in discrete amounts. The same light that appears smooth from a distance can reveal something almost granular up close. You are surrounded by this behavior every moment you are awake. Sunlight is striking your skin. Light is entering your eyes. Photons are being absorbed, scattered, reflected, and detected all around you. You normally experience only the finished picture, but underneath that familiar glow is a deeper physical process, one that refuses to fit neatly into the categories your everyday intuition gives you. The beam looks continuous. The individual interaction does not. And once you notice that difference, the simple picture of light begins to fall apart. The contradiction becomes sharper when you look at what experiments actually show. Light produces interference patterns. It bends and spreads through narrow openings. When two paths are available, the results can depend on how those possibilities combine. These are unmistakably wave-like behaviors. But when light transfers energy to matter, something different appears. In the photoelectric effect, for example, electrons do not absorb an arbitrary amount of energy from a dim, continuous electromagnetic wave. The energy exchange occurs in discrete amounts associated with the frequency of the light. So what is light? The familiar answer is, it is both a wave and a particle. That sounds satisfying, but it isn't really an explanation. It gives you two labels. It doesn't tell you what physical reality is doing underneath those labels. Light is not simply a classical wave that occasionally decides to behave like a particle. And it isn't necessarily a microscopic billiard ball flying through space, waiting to hit something. Nor should you imagine photons literally transforming back and forth, wave here, particle there, as though nature were switching between two ordinary physical forms. Those pictures are useful metaphors only up to a point. Push them too far, and they begin creating more confusion than understanding. The deeper idea is stranger, but also cleaner, and the remarkable thing is that you already have most of the pieces needed to understand it. The essential concepts were developed more than a century ago. Physicists learned how to describe waves, probabilities, energy, measurement, and the mathematical structure connecting them. What is rarely explained clearly is how those pieces fit together. Because the real mystery is not that light has two personalities. The mystery is why our everyday categories, wave, particle, object, trajectory, are simply not the right categories for describing what happens at the quantum level. Once you see that, the apparent contradiction begins to dissolve. But before we go any further, there is something we need to clear away, because this subject has accumulated a remarkable amount of bad explanation. Quantum physics is often introduced with a sentence that sounds profound. Light is both a wave and a particle. You may have heard it many times, and there is a reason the phrase survives. It is short, memorable, and points towards something genuinely strange. But taken literally, it can leave you with a picture that physics itself does not require. Then the explanation sometimes gets even more dramatic. You hear that light exists in two realities, that photons are literally tiny particles and invisible waves at the same time. Or, in some versions, that human consciousness somehow creates physical reality simply by looking at it. These statements can sound mysterious, but mystery is not the same thing as explanation. A good scientific explanation should tell you what the experiments show, what mathematical framework describes those results, and where our everyday intuition stops working. That is one reason the style associated with Richard Feynman remains so valuable. Feynman was not interested in making nature sound mystical. He was interested in finding the simplest description that survived contact with experiment, and he was comfortable admitting when an intuitive mental picture simply wasn't available. That intellectual honesty matters here. Classical physics encourages us to imagine that an object has definite properties of familiar kinds. A ball has a position. It has a velocity. You can imagine its trajectory existing whether or not you watch it. Quantum physics does not fit neatly into that framework. Instead, the theory gives us a mathematical structure for predicting possible outcomes. At its heart are quantities called amplitudes, whose relationships determine the probabilities of what we eventually observe. That distinction is crucial. The theory is not merely saying sometimes light is a wave and sometimes it is a particle. It is saying that the classical categories themselves are incomplete descriptions of quantum phenomena. The interference pattern is real. The individual detection event is real. The mathematical framework connecting them is real. But imagining a tiny classical object secretly carrying a little wave around with it is an extra story, and experiments do not require that story. So rather than asking which label light really is, we should ask a more precise question. What does the quantum description actually say about what can happen? Once you remove the slogans, the subject becomes much cleaner, and that is exactly the kind of science worth slowing down for. If you enjoy science explained without the hype, without mystical shortcuts, and without pretending that difficult ideas are simpler than they really are, this is the kind of question worth staying with. Here, the goal is not to tell you what to believe, because a famous physicist once said it. The goal is to follow the reasoning, look at what experiments actually reveal, and build the explanation one step at a time. Some of the most interesting parts of physics are also the parts that usually get compressed into a single sentence. And when that happens, the mystery can sound deeper than it actually is. So stay with the question. You don't need to memorize equations or accept a strange picture on faith. We can simply follow the evidence and see where it leads, because the closer we look, the more precise the mystery becomes. Now let's go back to the beginning of the mystery and follow what happens when light encounters an experiment. Start with the experiment that made the contradiction impossible to ignore, the double slit. Imagine a beam of coherent light directed toward a barrier containing two narrow openings. Beyond the barrier sits a screen. If light behaved simply like tiny classical particles, you might expect two bright bands behind the two openings. But that is not what happens. Instead, you can see a sequence of bright and dark regions. The bright regions occur where the wave amplitudes reinforce one another. The dark regions occur where they cancel. That is the familiar mathematics of interference. For visible light, the wavelengths involved are roughly 400 to 700 nanometers, far smaller than the width of a human hair. Yet those tiny differences are enough to produce a visible pattern across the screen. So far, the wave description looks extremely successful. Then slow the experiment down. Reduce the light intensity until photons reach the detector one at a time. Now something remarkable happens. Each photon produces a localized detection event, a single spot on the screen. You do not see a faint fraction of a photon spread across the entire detector. One event, then another, then another. If you watched only the individual impacts, you might be tempted to say, there are the particles. But keep recording. Hundreds of detections become thousands. And gradually, the same interference pattern begins to emerge. Individual events are localized. The accumulated distribution is wave-like. That is the point where ordinary intuition begins to fail. The quantum description introduces a quantity called an amplitude. It is important not to picture this amplitude as a literal substance flowing through space like water. It is a mathematical quantity used to calculate possible outcomes. And here is the crucial difference. Probability is related to the squared magnitude of the amplitude. In simplified form, P is proportional to the absolute value of A squared. The important part is that amplitudes can interfere before we calculate the final probabilities. Suppose there are two possible paths. Their amplitudes can reinforce each other in some places and cancel in others. If you tried to add ordinary probabilities directly, you would never reproduce the dark interference fringes. Quantum mechanics requires something more subtle. Now change the experiment again. Place a detector or other interaction capable of revealing which slit the photon went through. The interference pattern disappears when the paths become distinguishable. This does not mean that a conscious human mind magically changes reality. It means that the physical experimental arrangement has changed. Information about the alternatives has become available through an interaction with the system. And now we can connect this strange behavior to another famous experiment. The photoelectric effect showed that light transfers energy to electrons in discrete quanta. The energy associated with a photon is described by E equals hf, where h, Planck's constant, is approximately 6.626 times 10 to the minus 34 joule seconds, and f is the light's frequency. For visible light, that puts individual photon energies roughly in the range of 1.8 to 3.1 electron volts, depending on frequency. There is also a threshold. If the light's frequency is too low, increasing its intensity does not simply make electrons escape with arbitrarily accumulated energy. The frequency itself matters. This is why the classical picture of light as nothing more than a continuous electromagnetic wave delivering energy smoothly to matter is incomplete. Yet none of this requires us to imagine photons as microscopic billiard balls. The deeper description is quantum mechanical. Light travels according to a quantum theory that produces wave-like interference and particle-like detection events as different aspects of the same underlying framework. And the speed involved is extraordinary. In vacuum, light propagates at exactly 299,792,458 meters per second. But the important point is not simply how fast light moves. It is that nature does not appear obligated to behave like the familiar objects surrounding us. Wave and particle are classical categories. Quantum mechanics gives us a more fundamental mathematical description, and those classical words describe certain experimental features of what that description predicts. And this is where most explanations make the problem harder than it needs to be because they try to force the quantum world back into the categories of everyday objects. This is where a surprisingly simple mistake can make quantum physics seem far more mysterious than it needs to be. We instinctively want to choose. Is the photon a tiny particle traveling through space? Or is it a little wave physically spread out across the room? Both pictures feel familiar because both belong to everyday physics. But take either one too literally, and the double-slit experiment stops making sense. Imagine a classical particle passing through two openings. If each particle chooses one slit and follows one definite path, the natural expectation is simple. Two openings should produce two broad bands on the screen, no alternating pattern of dark and bright fringes. Now imagine a classical wave. A wave passing through both openings can spread, overlap, reinforce itself in some regions, and cancel itself in others. That naturally produces interference. But the quantum experiment gives us something neither classical picture captures by itself. The detector records individual, localized events. Yet when enough events accumulate, their distribution follows the interference pattern. So the mistake is not that we have failed to decide whether the photon is a wave or a particle. The mistake is assuming that it must be one of those classical things in the first place. A photon does not need to secretly choose a classical identity before the experiment begins. Instead, the quantum theory tells us what probabilities and correlations to expect for a particular experimental arrangement. Change the arrangement, and you can change what is measurable. Make the paths indistinguishable, and interference can appear. Make which path information physically available, and the interference disappears. The important question then is not, what is the photon, really particle or wave? A better question is, what does the quantum description predict for this experiment, and what do we actually observe? That may sound like a small change in wording. It isn't. It moves us from forcing nature into familiar categories to allowing the experimental evidence to determine which concepts are useful. And once you stop demanding that a quantum object behave like an ordinary object, the contradiction begins to look very different. So if the question, particle or wave, is already misleading, what should replace it? There is a belief almost all of us carry without ever being taught to carry it. If something is real, surely it must have one definite physical nature. A chair is a chair. A tennis ball is a solid object. A water wave is a disturbance moving through water, and this intuition is not foolish. It works extraordinarily well. For centuries, classical physics described the everyday world with remarkable success, so it was natural to carry those categories into the microscopic world. Then, experiments began to resist them. In 1905, Albert Einstein explained the photoelectric effect by proposing that light energy is exchanged in discrete quanta, an idea that helped establish the quantum description of electromagnetic radiation. Later, experiments involving diffraction, interference, and the double slit made another fact impossible to ignore. Light produces behaviors that classical particle and classical wave models describe separately, but neither model captures the entire phenomenon. The important step is not to conclude that a photon must therefore be two classical things at once. That conclusion simply preserves the old categories. Instead, quantum mechanics gives us a different framework. Think of it in 5 steps. First, your everyday intuition is reasonable at everyday scales. Second, quantum experiments reveal behavior that does not fit those categories cleanly. Third, calling light both a wave and a particle is a shorthand for different experimentally observed features. Fourth, the deeper quantum theory predicts those outcomes without requiring a literal classical wave and classical particle to coexist inside every photon. And fifth, the categories are the approximation, not the underlying reality. This is the belief that needs changing. You were not wrong to imagine objects having definite properties. You were simply applying an extraordinarily successful human-scale intuition to a domain where nature does not have to cooperate with it. So when physicists say that light behaves like a wave, they are pointing to phenomena such as interference and diffraction. When they say it behaves like a particle, they are pointing to localized detection and quantized energy exchange. Both observations are real, but they emerge from one quantum framework. Light does not have to secretly choose an identity, and it does not have to be two ordinary objects at once. The better question is what the quantum theory predicts and what the experiment reveals. Once you stop asking the photon to fit inside those two old categories, the practical way to think about the experiment becomes surprisingly simple. So how should you actually think about light when you encounter these experiments? You can use a simple 4-step framework. Step 1. Start with the experiment, not the metaphor. Don't begin by asking whether the photon is secretly a wave or a particle. Begin with what the experiment does. 2 slits, a detector, a light source, a screen. Keep the physical setup clear before adding interpretation. Step 2. Ask what is actually detected. In a single photon experiment, the detector records a localized event. That is something you can measure. You don't need to imagine a tiny glowing ball traveling toward the screen. Step 3. Separate individual outcomes from the pattern produced by many outcomes. One detection gives you one location. Repeat the experiment many times, and the distribution of those locations can form an interference pattern. That distinction is essential. The individual event and the overall statistical pattern are not competing descriptions. They are different levels of what the experiment reveals. Step 4. Treat wave and particle as descriptions of behavior, not necessarily competing identities. Wave-like language helps describe interference and diffraction. Particle-like language helps describe localized detection and discrete energy exchange, but neither word has to be taken as a literal picture of what a photon is made of. Return to the double slit. A photon produces one localized detection on the screen. Repeat that process again and again, and the probability distribution governing those detections produces the familiar interference pattern. Nothing has gone wrong. Physics has not failed to decide what light is. Rather, quantum mechanics has given us a framework capable of predicting both kinds of observations without forcing nature into an everyday mental picture. That is the real payoff. You don't need to memorize the slogan, particle plus wave. You need to remember the method. Experiment first, detection second, statistics third, classical labels last. Once you use that order, many of the apparent contradictions in quantum physics become easier to approach. And now return to that ordinary beam of light we began with. But this time, notice what you couldn't see before. You are back beside the window, watching that same quiet beam of sunlight cross the room. Nothing about the light looks different, but your understanding is. Behind that apparently continuous beam are quantum processes capable of producing individual localized detection events while generating interference patterns. Every day, countless photons enter your eyes and interact with matter around you. They never had to switch between being little particles and little waves. The mystery was never that light changes from one form into another. The deeper lesson is that our everyday categories were never large enough to describe the quantum world. And once you see light this way, an even stranger question naturally follows. If you enjoy uncovering what physics actually says beneath the familiar slogans, stay curious and keep following the questions with us. There is always another layer beneath the obvious answer. And sometimes the strangest questions begin with something as ordinary as light.